Today, we want to look at this thing called the tree, okay? And it's a nice progression from what we've been looking at because we started with this idea that an object can reference another object of the same data type. That idea of a reference, okay, to another object of the same data type allowed us to create the object known as the linked list. Once we had the linked list, we could build from that. So that was our singly linked list. What we actually did in class was something a little more complex, something that referenced both forwards and backwards, known as the doubly linked list. That's the one we actually coded. A little more useful because we were able to use that doubly linked list to create the objects known as the stack and the queue through inheritance, which were also similarly connected objects. We also talked in theory about these lists that could also both singly link back to the beginning instead of linking to null. And this was called a circular list. Actually, it's a circular singular list. And although we didn't program one, in theory, we could have also programmed one that's doubly linked, and the end node goes back to the beginning node, and the beginning node goes to the end node. And this is also a circular list, but it's a circular doubly linked list. So that was all the kind of theory we had at this point. But in all these situations, even the stack and the queue, these are all linear type creations. They all follow a straight line. Now the stack, you could argue, goes up and down, but it's still a line, okay? What I'm going to propose today is a similar structure. But this node, okay, is also going to have two references. So it's going to hold data, but instead of thinking of it as linking forwards and back, we're going to think of it as linking out two directions this way. And the beauty of this object is, if this is what we're going to create, just group it, shrink it. Then this object can be created in multiple places, like this. And this creates the so-called tree object, okay? So the idea with this object, the reason it's called a tree is the way you imagine it is that you've got the ground, and the tree usually grows up from here and out and branches out like that. That's the way we visualize a tree. Mika, don't criticize my art skills. So that's the idea, but we're going to take this object and flip it around, okay? That's the way you want to visualize the tree object, okay? Drawn more simply, it has a node that connects to nodes this way. Like that. Okay, so this is the tree object. It makes use of a lot of stuff that we've already been doing, but a lot of the inner logic that we're going to deal with this thing changes, okay? As well, we got to change up some of the terminology we use with this thing. These will still be called nodes. That still makes sense to call those nodes. But we're going to come up with names for the connections, okay? The connection between each node can essentially be called a branch, right? If we use the tree analogy. If we were using a math analogy, you could also call that an edge, okay? It's an edge connecting it. But I like the term branch. It kind of makes more sense in the tree analogy. As well, we also might not just call them nodes, but we can be more specific about the node, okay? Just like in the example on the previous thing, if I turn this back around to be an actual tree, Okay? The part where the tree hits the ground is often given a name. Actually, more accurately, it's sort of the part that's under the ground. We usually call that the root of the tree. Okay? And at most trees, at the very end of a branch, okay? So yes, this is a branch. And at the very end of a tree, we usually have a thing called a leaf, right? So the leaves are at the ends of the trees and the root is at the beginning. So in the realm of computer science, we've used that terminology. So this node right here is called a leaf node, okay? Because it's at the end of the tree. This node right here is called the root node because it lies at the beginning of the tree. That's the entry point into the tree. The tree starts here, it branches out, eventually reaching a leaf node, okay? Now similarly, I can have more branching occurring in different places, okay? And it could branch out from there, but that's some of the terminology we want to use. So that we're going to have these words leaf, root, node, of course, branch. Okay, so those are some of the terms you're going to hear me say in this unit. Okay? As well, the neat thing about trees is they kind of maintain the same properties all the way through the tree. So at this point in here, I can just take one portion of the tree, and I'm going to call that a subtree. And for that particular little subtree, it also has its own roots and leaves. So each inner part of the tree has the same properties as the whole tree. Now, if you think about that, what that can lead to is a whole different kind of logic than it's related to when we work in a line. What this can relate to is the fact that trees are going to use recursion. They can use recursion to up the logic here because each sort of portion of the tree is true for the whole tree. Okay, so there's some of the terms we're going to need. Now, for any particular node, any node, just somewhere in the middle of the tree, it could have something going in it, and it could have some things going out of it. Okay? Right? Like depending on where that node is on the tree. So it could have some branches going in. And it could have some branches going out. Okay? In tree studies, we do this by measuring what's called the in degree of a particular node and the out degree of a particular node. So the number of nodes going in this case it's 3, is its in degree. The number of nodes, or sorry, the number of branches coming out is its out degree, in this case 3. So now if I go back to the previous tree and I pick any particular node, this node for example, right here, it has an in degree of 1 going in, and an out degree of 1. What's true of every leaf node? Every leaf node, you know one of those values, no matter what. 0 what? Out degree, yeah. It'll have a 0 out degree, no matter what. So leaf nodes will always have a 0 out degree. We also know something about the root node. What's true of the root node? It'll always have an in degree of 0. Root nodes will always have a 0 in degree. But for any other node, it could be different, right? In this case, I've drawn what's called a binary tree because it all branches into 2s. But that's not the only kind of tree you can create. But in general, every root node will have a 0 in degree and every leaf node will have a 0 out degree. And that's actually how you can tell that those are the nodes. Okay? So Another term that you may hear me use is the term degree, in terms of in or out degree. Okay. Let me show you a little bit of what I have for the presentation for this. Okay. So you're going to see again some of this terminology, and it's important to grasp some of these terms as we start programming the tree. Because if you get the terms down, it's easier to talk about the tree in its sort of context. All right, come on. Come on, PowerPoint, you can do this. Okay, so some of these definitions are a little mathematical. Just sorry for everybody, I'm going to dim the lights here. So although we've been looking at linear ADT structures, the tree is a non-linear structure, okay? It's a hierarchical structure. It's a connection. In graph theory, the definition of a tree is a linked set of nodes that has no looping within it. Don't worry about graph theory. That's a little beyond the IB course, but we may even look at that this year. So in your IB curriculum, the type of tree you need to know is known as the binary tree. We will look in theory at some more complex trees beyond the binary tree, but that's the one you need to know. And I'll show you again, we looked a little bit at the curriculum last week. So trees represent relationships. So some of the other terms you're going to hear is parent and child, okay? So for example, A is the parent of node B and C. That's pretty simple. Node D is the child of node B, right? D is the child of B. Now we could extend that terminology further. We could describe B and C as siblings on this tree. We could use the term grandparents if we wanted to, or great-grandparents, but that gets a little convoluted. We don't need to necessarily get that detailed in our description of things. Just that we know that every tree has at least one parent or one root node, okay? And as well, every tree will have at least one or zero leaf nodes, okay? By the way, the root node can be a leaf node. A tree could have a value of 1, right? It could have a value of 0. Okay. So nodes that have no children are known as leaf nodes, as we can see here. So D, E, and C are all leaf nodes, okay? A is the ancestor of D, E, C, and B, okay? In degree and out degree, as I've already explained to you, are the number of nodes going, or sorry, the number of branches going in or the number of branches going out. As well, subtrees are portions of larger trees, and subtrees contain the same properties as the tree itself, okay? All right, so now let's switch to binary trees specifically. A binary tree is defined specifically as a tree that has either a single node, right, just one root, and a collection of subtrees within it. So the tree could be empty, or it could be partitioned into 3 distinctive subtrees. So the root, and the left subtree, and the right subtree, okay? Now let me kind of stop for a second and explain what I mean by that, okay? So let me redraw a binary tree, okay? So the basic value is you could have a binary tree. So now we're specifically talking about binary. So a tree could be empty. There could be no nodes. A binary tree could have 1 node. At that point, it would just be a root. That's it. But a tree could also be a collection of a root node and a left subtree, okay, or a root node and a left subtree and a right subtree. And that's it. That's the definition of a binary tree. Now keep in mind that each subtree holds the same definition. So for this subtree, it's either just a root, or a root with a left, or a root with a right. So a binary tree can be empty, just a root, and a left subtree, and a root, and a right subtree, or a root, and a left subtree, and a right subtree. So really that's the 5 different ways we can have a tree, right? So let me show you an example of all 5 of these. So there's the empty tree. That was easy to draw. There's just a root. There's a root and just a left subtree. Here's a root and just a right subtree. Okay? That's a whole subtree within it. Or a root and a left subtree and a right subtree. Okay? Those are the different sort of possible trees. Okay? So just an empty one. Okay? So 1, 2, 3, 4, 5. So this is type 1, 2, 3, 4. Sorry, that's 5 and 4. Okay? And keep in mind, when I say subtree, it's the same definition. So here, this is a root, and this one is a root and a subtree. This one is a root and a subtree, and this subtree right here maintains the same definition. So it's a root and a left and a right. So this is 4 plus 5 as the subtree. Okay, I think I'm getting a little confusing here for some of you, but your silence is worrying me. Okay, so that's the definition of a tree. Okay? It's defined as a full binary tree if every node is present at every level. So let me show you some examples. That's a full binary tree. It has 1 level, 1 node. That's a full binary tree. 2 levels, 3 nodes. Every node is present. That's a full binary tree. If, for example, this one was gone, that one right there was gone, it would no longer be a full tree. It would be a partial tree. Okay? This is a full tree. 4 levels, 15 nodes. Now, let's see how mathematical you guys are. Can you figure out a relationship between the level and the number of nodes? And I'm going to warn you, it's not an easy formula. So at 1 level, we get 1 node. 2 levels, 3 nodes. 3 levels, 7 nodes. So what's the relationship between 3 and 7, 4 and 15, etc.? Or x and y? It's hard. Okay, I'll give it to you. It's 2 to the L minus 1. 2 to the level minus 1. Okay, that's how you can determine the number of nodes. But it's related. It is a linear relationship. It is well, not linear, but it is a relationship that is mathematical. Okay? So that's the theory. So now we're going to program this thing. We're going to write code to do this. So if we go way back to here, when I first introduced it to you, this idea of a node, because it's all based on the node. So we're going to have a node that holds data, as I said before, and let's draw it out this way. Rather than call those next and previous, we're going to use better words for these. We're going to call this left and right. Okay? So our node will contain data, and it'll connect to the left tree and the right tree. Okay? What we can't then use is we can't use the node class that we've been working on. Because if you take a look at the node class within here, it uses the words next and previous. And that's not going to cut it. So we will have to build a second node class. So although we're almost out of time today, let's get started with that. And we're going to continue this within our big example. So we're going to put a node class inside our collections package called tree node. So we'll just make it a little more specific. So we're going to make a new Java file, new Java class called tree node inside of our collections package. Okay? Now, the question I want to ask you guys is, how complicated do you want this class to be? In other words, we could make this generics, like we did with the linked list example. Or, if we want to shorten up the code and shorten up these examples, We could make this just a simpler tree of, say, for example, just integers. So how many of you would like to do it simple, or how many are ready to just go for it at the level of generics? Generics? Where it's going to be hard, most of it is not going to be that hard. Where it's going to be hard is, what you're going to have to do with trees is you have to, unlike just regular nodes where you checked if two things were equal, with trees we have to check to see if one thing is less than or greater than. And how do we do that with things like strings? How do we check if they're less than or greater than? Is cat less than dog, etc.? So, and how do we do that with generic objects? How do we check to see if they're less than or greater than? So we can do that, we can code that in, but it is going to be a little bit tricky to do that, and it may not always work in all cases, okay? But I'm with you. Let's make this a generic tree node. So the data, public T data, will be generic. And we will have a connection to the left. Whoa. And the right. This is different than our other node class, which connected to previous and next. We are now connecting to left and right. Okay, and we're going to stop there for today.